Warm greetings to my CCE 204 family. This is Kami coming to you again from the deserted downtown Kingston. Today, we are going to up our game when it comes to primary and early detection of chemical warfare agents. By that, we mean detectors that are placed at the perimeter of bases or close proximity of troop concentrations that can give an adequate and early alarm, so in case of chemical warfare attack, troops have enough time to deploy their individual protective equipment. In that, ionization detectors are such detectors. They are the most commonly deployed detectors by all armed forces in the world, including Canadian Armed Forces and US Army. In fact, US Army deployed ionization detectors as its most important chemical detection capability in the Operation Desert Shield or Desert Storm, otherwise known as Iraq War, in 1990-1991. In civilian world, these detectors carry out a lot of functions. Detection of toxic industrial chemicals, illicit drugs, or explosives. So as I said, these detectors are early detectors. In other words, primary screening detectors. For that, they have a fast response time of less than a minute, and they can detect chemical warfare agents in the form of vapor and or fine aerosol. Obviously, because they're primary detectors, they should have high sensitivity. In here, ionization detectors are listed as having a lower limit of detection for nerve agents of 0.1 to 0.2 milligram per meter cube. And for mustard, that lower limit of detection is 10 milligram per meter cube. Lower limit of detection, as is listed here, means only one thing, that below those numbers, these detectors are not reliable. But they also suffer, these ionization detectors, from low specificity in the fact that if they are deployed near engine exhausts of all kinds of engine, they will produce false alarm. This is no different than at your home when you open the oven door, your smoke detector or fire detector at home goes off. In fact, your home smoke and fire detector is based on the same technology, that it has a radioactive source in it that produces beta particles. Now, how does this technology work? Let's look at this together. In here, you see an air chamber that is surrounded by a power source, anode and cathode, positive and negative of a battery or another power source. That radioactive source that I referred to a little earlier produces a lot of beta particles. These beta particles are constantly bombarding the air that is in that little space. And by bombarding the air with those beta particles, as you see here, you produce a bunch of charged species. Like the beta particle knocks the electron out of nitrogen or oxygen of air. So therefore you have an electron. That electron carrying a negative charge is attracted to anode, which is positive, and the remainder of the molecule, which is now positively charged, is conversely attracted to the cathode that is negative. Now, that is a continuous motion, whether this is a chemical warfare agent detector or your smoke detector at home. That continuous attraction of negatively and positively charged particles that are produced as a result of beta bombardment of molecules of air produces a current. Now let's look at this. In here you will see that those positive and negative charges that are continuously produced produce a certain voltage. Now imagine, in your ionization detector or smoke detector at home, if smoke was produced and reached that chamber, or a chemical warfare agent entered the chamber, both those ideas interfere with the traveling of those plus minus charges and produce a different voltage. That different voltage sounds the alarm. Let's move on to another very sophisticated detector, which is referred to as flame photometry detectors. The picture is in front of you, and on the lower left hand side you will see an air intake. The air enters this detector, but in here you have a flame that burns at 3200 degrees Celsius. Yes, that is a hot flame. That is a very high temperature. Hotter than what the temperature that they produced your Kentucky Fried Chicken. With these kind of temperatures, the atoms that are sucked into that air inlet are energized. Energized atoms give off or emit light. Those lights are very particular from each atom. In other words, phosphorus produces a wavelength of 526, and sulfur produces a light with a wavelength of 394. Now you appreciate the fact that mustard and nerve gases all have sulfur and phosphorus. So when those wavelengths are produced, they are a clear indication of the presence of those chemical warfare agents in the vicinity. The detector shown here weighs 2.3 kilograms or 5 pounds. You know, one of those little plates in the gym. Response time, respectable, 30 seconds or less. Again, here we go again. Lower limits of detection for nerve agents under 0.05 milligram per meter cube, and for mustard under 0.5 milligram per meter cube. Again, those are lower limits of detection, below which this detector may not be so reliable. Let's look at another class of detectors, which are infrared detectors. Folks, I'm going to now change my screen in order to make a point. All molecules vibrate like this. you can see here a water molecule vibrating. Molecules vibrate in all temperatures except when the temperature reaches minus 273 Celsius. Now that's cold. But in all other temperatures, molecules vibrate like this, and that vibration produces an infrared or IR radiation. That radiation has a specific wavelength associated with it. In other words, every molecule that vibrates produces an infrared with a specific wavelength, and that specific wavelength is like a fingerprint of that molecule. Mustard and nerve gas, they have molecules. Those molecules vibrate and produce a specific IR radiation that is their fingerprint. In other words, it's exclusive to them, just like your fingerprint or your DNA that is specific to you. Now, let me elaborate or demonstrate better what do we mean by a fingerprint. Let's look at this. You recognize this as Sarin or Gb, and a molecule is shown on the top. An IR spectrum of Sarin is shown below on the lower left hand side, and you can see a peak produced at a specific frequency or wavelength. That is the fingerprint of Sarin. That is not shared by any other molecule. Now, how does this fingerprint produced? Well, look at this. Sarin also vibrates, and that vibration is very specific between the oxygen and the phosphorus atoms, vibrating in the manner shown in here. That vibration is very specific, and it produces that fingerprint. Now, that fingerprint from Sarin is different than the fingerprint shown here from mustard. And you can see that the fingerprint of mustard is quite different than Sarin, and that peak appears at a different frequency and wavelength, and the pattern is different, just like you have a fingerprint and you have a specific DNA to you. Now, I want to impress you by this, which is called CATCEDM, standing for Compact Atmospheric Sounding Interferometer Engineering Development Model. Yes, folks, this is the pride and joy of Defense Research and Development Canada, DRDC, Valcartier, Quebec. 100% Canadian ingenuity. And are you ready for this? This can detect those vibrations of chemical warfare agents from 5 kilometers away, giving you a lot of time to react with 95% plus confidence. That's impressive. Thank you, DRDC Valcartier. I hope you are staying strong and impressive. Thank you so much. Keep those comments coming.